We're going to take a look at writing word equations and balancing chemical equations today, okay? So let's go over a couple of things. In the late 1700s, Joseph Priestley performed a chemical reaction that led to the discovery of oxygen. And what happened was he took this deep red powder, which was mercury 2 oxide. Powder is a solid. Mercury 2 oxide is HGO, and we know that because mercury 2 would be Hg plus 2, oxide would be O negative 2, and if you're making a neutral compound, you would need one of each ion to make HGO, okay? The solid, the little S that's in parentheses after it, that indicates its state of matter. So when they say it's a powder, that's why you put S to represent that it's a solid. And when this was heated, it ended up producing a liquid that was silver, and that was liquid mercury. Mercury is Hg. You'll notice they put a little L. The L is often italicized to represent a liquid in parentheses after it. And then they also produced oxygen. Oxygen is diatomic. That's why you see it represented as O2, and it's a gas. And it's a odorless, clear, colorless gas. Okay? So this first thing on top here is your word equation. That's where we use the names to produce an equation of what's happening. The formula equation uses the chemical formulas and the states of matter if we know what they are. Okay? On the left-hand side, whatever you start with, those are the reactants, so those are to the left of the arrow, and whatever the new substances you form to the right of the arrow, those are called the products. Okay, let's take a look at the next page. Okay, on the next page, they reiterate the different states of matter. So here you'll notice that they tell you that an S in parentheses after formula represents a solid. An L in parentheses is a liquid. A G in parentheses is a gas. And if you see the symbol AQ after a chemical formula, that stands for aqueous. Aqueous means that that substance is dissolved in water. So solutions will have an AQ after them because they are dissolved in water. Okay? Okay, now, the reaction that I told you about on the previous page is illustrated here in this figure. So here are the reactants. We have our solid mercury 2 oxide, which was a deep red powder. That's what they're showing you here in the test tube. They're heating it over a Bunsen burner. You're going to produce products, which would be oxygen gas, which is a clear, odorless, colorless gas. And that gas would leave the test tube. And then the liquid mercury is this little silvery substance that's at the bottom of the test tube. Okay? The reason I'm going over this is because anytime a chemical reaction happens, you're going to be looking for evidence of some sort of a chemical change. We've actually gone over this before in a couple of labs that we've done. So let's take a look at the different forms of evidence for a chemical reaction. So you definitely want to memorize these, okay? So some examples of evidence of a chemical change would be if it absorbs or releases heat. So what that means is while you're holding a test tube or a beaker and you mix things together, if it feels cooler or it feels warmer, that would be absorption or release of heat, okay? Color change. The color change would be unexpected. Obviously, if you mix yellow and blue, you get green. That's expected. But if you mix two things maybe that are colorless and all of a sudden it turns pink, that would be an unexpected color change. That would be evidence of a chemical reaction. The third one would be evolution of gas. All this means is that you are producing a gas. You will see bubbles if you're mixing two solutions together. When we did a chemical reaction where we combined baking soda and vinegar, do you remember how it bubbled violently in the container? that was a gas that was being produced. That was evidence of a chemical reaction. If you mix a couple of solutions and you make a solid, typically what happens is it will appear cloudy, and then that solid will settle to the bottom, and that solid is called a precipitate. And a precipitate could be a number of colors. It could be white, black, gray, yellow. It just depends on what you're mixing, okay? Why don't you take a look at the quick check with the person sitting next to you, and let's see what you guys come up with.
Yeah. Color change. This one kind of smells like something's burning. Like, I don't know what it
The
is.
heater was on,
Okay.
and it smelled like every time they turn the heater on, like in the winter, like for the first time, it smells like something's burning.
Oh.
And you were sitting like right under it.
Yeah, that was like
It was a-
okay.
I think it was the heater.
Okay.
Yeah.
Absorption or release.
Let's go over one really quick. Give me one of the forms of evidence that you guys listed. Yeah.
Color change.
Color change. Good job. Okay. What else would we put?
Evolution of a gas.
Yes, evolution of gas. Now be really careful when you are heating something. Like, just because you're heating something doesn't mean that you're going to put that its temperature is increasing. If you're mixing things and like it spontaneously gets warmer, okay, or spontaneously gets cooler, that would be a form of evidence that a chemical reaction took place. Not, oh, I'm heating it, therefore that's a chemical change. Does that make sense? Okay, so there's one not so. These are the two obvious ones for you. Okay, so what I would do also here is if you're losing or producing a gas and it's an open container, would the mass increase or decrease? Decrease because the oxygen is leaving. Okay, so even though this wasn't listed up above, you could say that the mass of the contents decrease, and this is not a common thing, but this is if you were doing a lab and you were trying to figure out if you were producing a gas. If the mass of the contents decreased, then that means a gas was produced and that substance is leaving. Does that make sense? Okay, but these two are the most obvious for you forms of evidence. For number two, I kind of want to do this with you. Here they want you to convert this into chemical formulas. So it's been a while since we've done nomenclature, so let's review this. Calcium oxide powder. What is the charge on calcium? +2. What's the charge on oxygen? -2. So if I'm writing the chemical formula for calcium oxide, what would it be? CaO, because you would need one of each so that those charges add up to 0. If it's a powder, what's the state of matter? Solid. It's combined with, so you're going to put a plus after that. It's combined with water. Water is H2O. Water's a liquid. I'm going to put a little L after it. We're forming calcium hydroxide solid. The charge in calcium is a +2. Hydroxide is on the bottom left of your periodic table. Remember, hydroxide is OH, -1. What would the chemical formula be for calcium hydroxide? Yeah, CaOH2. What would I do with the OH? Put it in parentheses because you've really got two hydroxides. Okay, anytime you have a polyatomic ion, which hydroxide is, you have to put it in parentheses if you're writing more than one of them. This is a solid, so I put a little S after it. Does that make sense what I just did? Okay. All right, now, number 3 wants us to convert a formula equation to words. So why don't we do the products first? Because the products are relatively easy. What would you call CO2? Carbon dioxide. So carbon dioxide. And what's the state of matter on it? What's this little G? Gas. So we've got carbon dioxide gas and what is H2O? Water. And you can say, and water. Okay, so those are my products. So I'm going to say to produce carbon dioxide, gas, and water. Okay, so now let's figure out what this reactant is. This is an acid. Acids begin with hydrogen. They're dissolved in water. You have to identify what this is called, what that polyatomic ion is called, because I need to know the ending, because this is a oxy acid. I need to know the ending so I can actually name it properly. So what is the name of CO3 on the right-hand side of your periodic table? If you don't actively look at the periodic table while we do this, this will not come naturally for you because you're not practicing it. Carbonate. Perfect. Okay, so CO3 negative 2 is the carbonate ion. Okay, if it ends in 8 on the bottom right of your periodic table, it tells you what to do. If it ends in 8, then what does it become? Yeah, it becomes ic acid. So this is carbonic acid. So carbonic acid decomposes to produce carbon dioxide, gas, and water. It's not so obvious right now for you to use this word decomposes. It will be after I do the next section. Okay? Yeah, question.
Where did the 2 hydrogens go?
Oh, so since all acids have a hydrogen, if I have a +1 and a -2, wouldn't I need 2 of these hydrogens to make a neutral compound? That's where the 2 came from. Okay? All right, are we good with this? Okay, so let's go on to balancing equations. So what we're going to do now is we're going to talk about Antoine Lavoisier. So Antoine Lavoisier performed experiments and he liked to measure volumes and masses of chemicals. Okay, that was his thing. And he formulated something called the law of conservation of mass. The law of conservation of mass says the mass before and after a chemical reaction happens has to remain constant. So if you have a chemical reaction in a closed container, the mass before and after will be the same. In order for us to follow that, what we have to do is we have to balance reactions. So let's go to the next page. And what we're going to do is we are going to place coefficients in front of the different chemical formulas that we have, and they will be whole numbers, and those whole numbers will get distributed to whatever is in the chemical formula after them to make sure that the number of atoms of each reactant is the same as the numbers on the product side, okay? And we're going to start with something like, let's go to the quick check on the next page, okay? So on the next page, right here, let me take a look at number 1 with you.